Right now, the universe you are living in is stretching. Every galaxy, every cluster of matter is pulling away from everything else at a specific, measurable speed. That speed is not just an academic detail. It is the most fundamental number in cosmology. If you know that speed, you know everything. You know exactly when reality was born, and you know exactly how it will end in the dark. If we have that number wrong, we have everything wrong. The universe you think you live in does not exist. For nearly a century, we built observatories on mountain peaks and launched satellites into the vacuum of space to find it. Recently, we finally succeeded. We measured the expansion of the universe perfectly. Twice. Using two completely independent methods. Both rigorous. Both trusted. One said 67, the other said 73. The universe refused to give us the same answer twice, and nobody on Earth can explain why. Two perfect measurements, two different universes, and we are trapped inside whichever one is real. Let's begin. There is a light that permeates everything. It does not come from a star, and it does not come from a galaxy. It is the cosmic microwave background, the oldest light in the universe. It was released roughly 380,000 years after the Big Bang. Before this moment, the universe was a dense, blinding fog of plasma, so hot that light itself could not travel. But as space expanded, it cooled. And when it cooled enough, electrons bound to protons. Atoms formed. When atoms first formed, the universe became transparent. The light from that exact moment was finally free to travel. It has been traveling ever since. For 13.8 billion years, it has crossed the expanding void, cooling and stretching, until it became a faint microwave hum, hovering just above absolute zero. Between 2009 and 2013, the European Space Agency's Planck satellite sat in deep space and mapped this light. It stared at the ancient radiation for years, measuring temperature fluctuations so microscopic they barely existed, differences of millionths of a degree. These tiny temperature shifts are not random. They are the acoustic echoes of the early universe. By reading them, physicists can see the exact recipe of creation. They can calculate the precise proportions of normal matter, and dark energy that existed at the dawn of time. Cosmologists took this recipe and plugged it into the standard model of cosmology. They took the physics of the early universe and ran the equations forward, spanning 13.8 billion years of cosmic evolution to predict what the universe should look like today. The model produced a prediction. It stated that today, the universe should be expanding at a rate of 67.4 kilometers per second per megaparsec. A megaparsec is a unit of distance. It is 3.26 million light years. The math was telling us that for every 3.26 million light years of space between us and another galaxy, that galaxy is receding 67.4 kilometers per second faster than the one closer to us. It was a rigorous derivation from fundamental physics. The standard model that produced this number is the same model that correctly predicted the abundance of hydrogen and helium in the cosmos. It is the same model that explains how galaxies form and cluster. It has been tested. It has been verified. It gave us 67.4. This is the blueprint. If the blueprint says 67.4, we should be able to look out our window, measure the galaxies moving away from us right now, and arrive at the exact same number. To do this, we use the cosmic distance ladder. The foundation of this ladder was built in 1908 by a woman named Henrietta Leavitt. She was working at the Harvard College Observatory, employed as a computer to catalog photographic plates of stars. She was paid 30 cents an hour. She was deaf, and because of the conventions of the time, she was not allowed to operate the telescopes herself. But looking at the glass plates, she discovered something fundamental about how the universe breathes. She studied a specific type of star called a Cepheid variable. These stars do not burn with a steady light. They pulse. They swell and contract, brightening and dimming in a regular mechanical rhythm. Imagine a star 10 times the mass of our sun, physically heaving. Millions of miles of burning plasma expanding outward into the vacuum, cooling, and then collapsing back inward under its own crushing gravity, over and over again. Leavitt realized that the rate at which a Cepheid pulses is directly tied to how luminous it truly is. A star that pulses slowly is inherently brighter than a star that pulses quickly. If you look at a Cepheid variable in a distant galaxy and time its pulse, you know exactly how bright it actually is. You compare that true brightness to how dim it appears in our sky, and you can calculate exactly how far away it is. A century later, an astronomer named Adam Rees and his team, known as SHOES, built upon Leavitt's foundation. Rees is not a fringe figure. He won the Nobel Prize in Physics in 2011 for the discovery of dark energy, the force driving the acceleration of the universe, using observations of distant supernovae. He and his team spent years meticulously building the cosmic distance ladder. They found Cepheids in nearby galaxies. They calibrated those Cepheids against type 1a supernovae, exploding white dwarfs that burn with a uniform, predictable brightness, allowing us to measure distances even further out. Each step calibrates the next, building outward from the local universe. It is the most precise tape measure Cosmology has ever assembled. Rees and the SHOES team used this ladder to measure the local expansion rate of the universe. They calculated how far the nearby galaxies were, and they measured how fast they were receding. They did the math. They expected it to confirm the blueprint. They got 73, not 67.4, 73, nearly a 9% difference. In a field that demands 1% precision, a 9% difference is not a rounding error. It is a structural problem. It is a gap large enough to hide an entirely new branch of physics. Rees went back through the data. He checked the calibrations. He checked the Cepheid measurements again. He looked for the flaw in the ladder. He waited for someone to find the mistake. No one did. Over the next decade, the SHOES team refined the data again and again. They added more galaxies, more Cepheids, more supernovae. They sharpened the tape measure until there was no room left for mechanical doubt. The number did not move. Other teams tried different methods entirely. They bypassed Cepheids. They looked at red giant stars. They measured the surface brightness of distant galaxies. The numbers they got were not all the same. Some landed close to 73, some came in closer to 70. None of them landed at 67.4. The ladder kept pointing higher than the blueprint allowed. The discrepancy slowly deepened until it reached 5 sigma. In particle physics and cosmology, 5 sigma is the gold standard for a discovery. It means there is a roughly 1 in a million chance that the data is a statistical fluke. It means the result is real. It was not a measurement error that anyone had been able to find. The local universe is expanding faster than the early universe predicts it should be. And nobody could explain why. For years, most cosmologists assumed the local measurements had to be wrong. It was the most rational position to take. The standard model of cosmology had been right about almost everything else. It explained the Big Bang. It explained the cosmic microwave background perfectly. It mapped the abundances of light elements and accurately predicted the formation of large-scale structure across billions of light years. It could not be the model. The model was too successful. It had to be the tape measure. The most popular explanation among theorists was cosmic dust. Cepheid variables are massive, young stars, and they tend to live in the dense, dusty spiral arms of active galaxies. When the Hubble Space Telescope looked at these stars across millions of light years, it was looking through a haze. The theory was simple. Hubble's cameras might be blurring the light of nearby stars together with the Cepheids, or the dust was altering the light, making the Cepheids appear brighter than they actually were. Brighter Cepheids look closer than they really are. Closer galaxies imply faster expansion. If we could just see through the dust, if we could isolate the Cepheids with perfect clarity, the discrepancy would relax. The 73 would drop down to 67.4. The tape measure would align with the blueprint, and the universe would make sense again. This was the hope. This was what the James Webb Space Telescope could finally test. The James Webb Space Telescope launched in December 2021. It cost $10 billion. It took nearly 3 decades of development. It is the most precise scientific instrument ever built by human hands. It possesses a 6.5-meter golden mirror, suspended 1 million miles from Earth, staring into the void. And it was built to see infrared light. Infrared light slices through cosmic dust, where visible light cannot. For this story, it had one job: see whether the dust was the problem. In 2023, the data started coming back. Adam Rees pointed JWST at the exact same galaxies Hubble had measured. He looked at the exact same Cepheid variables. He stared through the dust with the most precise infrared instrument in human history. The Cepheids did not look brighter. The distances did not change. The local expansion rate held at 73. Webb confirmed the discrepancy almost exactly. The dust was not the culprit. The tape measure had held. In early 2024, Rees and his team published the result in the Astrophysical Journal Letters. They detailed the observations, the removal of the dust interference, and the validation of the distance ladder. His statement was careful. With measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe. At a 2019 conference at the Kavli Institute for Theoretical Physics, before the JWST data even arrived, Adam Rees asked David Gross a question. David Gross is a Nobel laureate in particle physics. Rees asked Gross how particle physicists would describe a discrepancy this size. Gross's answer was direct. They would not call it a tension, and they would not call it a problem. They would call it a crisis. That word was not casual. Gross has spent a career inside the structure of fundamental physics. He knew what he was saying. When the blueprint and the tape measure are both perfect, but the numbers do not match, you can no longer blame the tools. You have to blame the foundation. The standard model of cosmology is not wrong about everything. It still explains the cosmic microwave background. It still explains the formation of galaxy clusters. It still explains the abundance of light elements. But it is missing something. Several theories are now being tested in the dark. The first is early dark energy. It suggests a brief, violent burst of expansion occurred in the first few 100,000 years after the Big Bang. A sudden injection of repulsive energy that altered the size of the universe early on, leaving a permanent fingerprint on the expansion rate today, before vanishing entirely. If this is true, it means the universe is haunted. It means phantom forces can flood the cosmos, warp the architecture of reality, and then delete themselves before we can ever see them. It means the machine is unpredictable. The second theory suggests a modification to gravity itself. It posits that Albert Einstein's general relativity breaks down at the largest cosmic scales. If this is true, gravity is not a universal law. It is a local illusion. It means the fabric of reality bends differently depending on how deep into the dark you look, and the universe is fundamentally unknowable. Or a third possibility, the most uncomfortable one, that the universe is not broken at all, that we are simply trapped inside something that distorts our view of it. The trouble with the Hubble tension is not just a broken equation. It is what that number demands we accept. If the local universe is expanding at 73 instead of 67.4, it means the galaxies around us are fleeing into the dark significantly faster than we expected. And that speed compounds. The universe is not just expanding, the expansion is accelerating. There is a boundary in the deep dark called the cosmic horizon. If a galaxy is pushed beyond that line, the space between us is expanding faster than the speed of light. The light it emits today will never, ever reach Earth. It crosses the threshold, and it is permanently deleted from our sky. Whatever phantom mechanism is driving that tape measure to 73 is the exact same engine that will eventually close the horizon completely. Every single second, entire galaxies slip over the edge. And eventually, this accelerating void will destroy the very tools we use to measure it. As billions of years pass, the distant galaxies will recede into the black. The Cepheid variables, our tape measure, will be pushed beyond the edge of reality. And the cosmic microwave background, the ancient blueprint itself, is stretching. Eventually, the expansion of space will stretch those microwaves so far that they will flatline. The blueprint will disappear completely. Any civilization that rises in the deep future of our galaxy will look up into an absolute, unbroken black. They will see the stars of the Milky Way and nothing else. They will have no tape measure and no blueprint. They will look at the dark and they will believe they are the only things that have ever existed. The universe is going to erase all evidence of its own history. The ultimate tragedy of this expansion is not just that they will be alone. It is that they will look at a static, empty room and believe they understand it perfectly. We do not know what is making the universe expand faster than the equations allow. We have theories. Each one asks us to give up something we believed about reality. Either the early universe was not what we thought, or the laws of gravity are not what we thought, or our place in the universe is not what we thought. The James Webb Space Telescope was supposed to settle this. It was supposed to be the witness that confirmed the model we built was the universe we lived in. Instead, it confirmed the disagreement. And then it kept looking. It looked deeper into the dark. It looked back further than any instrument had ever looked, into the first few 100 million years after the universe began. We had imagined that place as quiet, a slow accumulation of the first hydrogen, the ignition of the first dim stars, the patient, gradual assembly of the first faint galaxies over billions of years. Webb pointed at that quiet place and found something else. There were already galaxies there. Massive galaxies, structured galaxies, galaxies that should not have had the time to exist. We thought we had found one crack in our picture of the universe. We had found the first of several. But the era of certainty is over. We spent a century building the most perfect mirror in human history. We pointed it into the dark, expecting to see our own brilliant math reflected back at us. Instead, it showed us a universe pulling itself apart. We are not the architects of reality. We are just passengers, holding a broken tape measure in the dark, watching the walls